Example 4. Find the equation of the tangent line to f of x equals 2e to the x at x equals 0. So remember, to find the equation of a line, we're going to need a point and a slope. Our point we get by taking our x value and plugging it into the original function. Because again, this is the one point that's shared by both the function and the tangent line. This is where the tangent line touches. So when we plug in 0, we have e to the 0 power. Anything to the 0 power is 1, and 1 times 2 is 2. So that means the point where our tangent line is going to touch our function is the point 0, 2. We also need the derivative at 0, because the derivative at 0 is going to tell us the slope of the tangent line. So to get the derivative at 0, we first need to find the derivative. So our function here is 2e to the x. Constant multiple rule says the 2 is going to multiply the derivative of e to the x, but the derivative of e to the x is e to the x. So again, we're going to have 2e to the 0, which is 2. That's the slope of our tangent line. So putting this together, we have y equals 2x plus b. This is the slope. And then we're going to plug in our point 0, 2. So when x is 0, y equals 2. So that tells me that b equals 2. So the equation of my line becomes y equals 2x plus 2. So the equation of the tangent line that touches at the point 0, 2, it touches the function 2e to the x, is 2x plus 2. Let's do another one. Example 5. Find the equation of the tangent line to f of x equals 3 natural log of x at x equals 1. So again, to get the equation of the line, we're going to need the functional value at 1, and we're going to need the derivative at 1. So the functional value at 1 means we're going to plug 1 into the original function to get the y value. The natural log of 1 is 0, and 0 times 3 is 0. So that means the point where our tangent line touches is going to be at the point 1, 0. We also need the derivative at that point, as that will tell us the slope of the tangent line. So the derivative of 3 times the natural log of x is 3 times 1 over x. Plugging in a 1, we get 3 times 1 over 1, which is going to give us 3. That's the slope of our tangent line. So then we have y equals 3x plus b. We're going to plug in our point 1, 0. So here we're going to get 3 times 1 plus b. So subtracting the 3 over, I get b equals negative 3. So the final equation of my tangent line is y equals 3x minus 3. So again, being able to find the derivative is going to help us to figure out the slope of our tangent line, which will then allow us to find our actual tangent line. Let's look at a more applied problem of how these derivatives of natural logs and exponentials might come up. Example 6. When money is invested, it gains value depending on a lot of different things. One of the important factors is how money is compounded, which is how often the interest is added to the principal amount. If the interest is added one time per year, we say that it's compounded annually. The equation for annual compounding is given by f of v equals pv times 1 plus r to the t, where fv is future value, so how much you'll have at the end of your investment. PV is present value, or the amount you initially invest. R is going to be the interest rate, and we're going to enter it in decimal form, and time t is going to be given in years. We're going to use this idea to look at some things about money and see how this type of exponential function will relate to the derivatives we're learning. Part A. Suppose you invest $1,000 in an account that has an interest rate of 2.5%. How much money will be in the account in 5 years? There's nothing in this problem that says anything about a rate. In fact, we're just going to be doing a direct computation. If we're investing $1,000, that's a present value, the amount we initially invest. We want to know how much we'll have in 5 years. So that's a future value. So we're going to be using future value equals 1,000, that's our present value, 1 plus r. My rate here is 2.5%. To turn that into a decimal, I write 0.025 to the t, but my t here is 5 years. So my future value can be found by computing all these numbers very carefully in my calculator. So I punch them all in, and my future value on this investment is going to be $1,131.41. All of these examples are talking about money, so we're going to attribute the dollar sign when we talk about the answers. I'm also going to round to 2 decimal places because our currency system allows money to go out to 2 places. Another way to compound money is monthly. So this is something you may see when you go to the bank, a monthly checking rate. That's how typically savings and investment accounts work that are common at banks. That means that once a month, interest is added to your account. However, you do not receive the interest rate each month. You don't get 2.5% every month. Instead, the interest rate's divided up by 12, and each month you get a little chunk or 1/12 of that 2.5%. So the formula for monthly compounding is given by future value equals present value times 1 plus r divided by 12 times raised to the 12 times t. So we're doing r divided by 12 because we're dividing our interest rate into 12 applications. And then, since we're doing it 12 times per year, we're raising it to the 12 times t. So part B, assuming the same initial investment amount, interest rate, and number of years as part A, calculate the future value. Do you expect it to be the same as part A? Do you think it'll be bigger? Do you think it'll be smaller? Take a guess. Pause the video, write down your guess, and then we'll calculate it together. So here, plugging in all my numbers really carefully, I get future value equals, now my initial amount is $1,000, and I'm going to do 1 plus 0.025 divided by 12 raised to the 12 times 5. I'm going to carefully enter all these numbers into my calculator. Again, try to be careful with your calculations and your parentheses and things like that. And I'm going to get $1,133, even if I round to 2 decimal places. So it is a little bit more. So by getting my compounding to be done monthly, I actually end up with about $1.59 more than if I had done it annually. And that may not seem like a big deal, but if you're someone who invests millions of dollars, that can add up really, really quickly. So now that we have a sense of the difference between annual compounding and monthly compounding, let's look at some examples of how we're going to apply the derivative. Part C. For each of these general formulas, find a function that represents the rate at which the future value is changing. Keep in mind that t is your variable and PV and r are constants. So let's start with the first function we had, which was future value equals present value times 1 plus r to the t. Since t is our variable, that means if we're going to take the derivative of this function, it's an exponential function because we have a number raised to t. So we can write the derivative like this, f prime of v. Now, PV is a constant, so this is a constant multiple situation. So PV is going to multiply our derivative here, and the derivative of an exponential says we're going to get the same thing back times the natural log of the base. And my base here was 1 plus r. Now let's take a look at the other equation. So our second equation said future value is present value 1 plus r over 12. This one's a little bit trickier because for an exponential function, the rules we have so far talked about having it raised to t, not 12t or some other constant times t. So we have to do a little creative algebraic rewriting so that we can use our rule. So I can rewrite this function as PV times 1 plus r over 12 to the 12th, all raised to the t. Because remember, if you raise a power to a power, you're going to multiply them together, which means if you have 2 things multiplied together in a power, you can separate them as a power raised to a power. The reason this is helpful is because this here, 1 plus r divided by 12 to the 12th, right, is going to be a number in itself because r is the interest rate, right? And so all of that is a constant number. So the derivative here, again, FV prime, is going to be PV from our constant multiple. That number is going to multiply our derivative. And we're going to multiply that by 1 plus r over 12 to the 12th to the t. So we get the same thing back times the natural log of the base. And my base here is going to be 1 plus r over 12 to the 12th, because that's the constant part of that function. So we found a way to write the derivative of how quickly our investment is changing, knowing that the variable is t and knowing how to take derivatives of exponentials. For part D, it wants us to explicitly calculate the rate at which each function is changing if time equals 3, present value equals 1,000, and the rate is 0.025. So what we need to do is go back to our derivatives and plug in these values. So here, if we want to find the rate at which the future value is changing, we'll plug in 1,000, 1 plus 0.025 cubed times the natural log of 1 plus 0.025. So we plug in all those numbers, we carefully crunch that number in our calculator, and we get 26.59. And that's going to be in dollars per year. So remember, our independent variable t is time, and time was given in years, and our dependent variable is future value of your money, and so that's going to be in dollars. So that means that my investment is increasing by $26.59 per year when it's been 3 years. Let's do the same thing for our other derivative when we're compounding monthly. So again, we're going to carefully plug in our values. So we have 1,000 times 1 plus 0.025 divided by 12 raised to the 12th, all cubed, times the natural log of 1 plus 0.025 divided by 12 to the 12th. Close the parentheses there. Again, we're going to carefully plug everything in. And when we crunch that number, we get that we're increasing at approximately $26.92 per year. So dollars per year. So again, it's really useful to know how much we're increasing and which one's a better scenario for us. We can see here that when we compound monthly, the rate at which our investment is increasing is slightly higher than the rate when we're annually compounding. So when you go to do your investments, if you have the choice between annual compounding and monthly compounding, monthly is going to get you a little bit more money. And the more money you invest, the bigger difference this makes. And we're able to use derivatives here to figure out how quickly our investment was changing because we were able to calculate the rate of change of an exponential function using our derivative rules.